Hello everybody, and welcome to your linear algebra review on solving a system of equations using inverses. My name is Jason, and I work for the ASU Tutoring Centers. Now, if you haven't seen the previous videos, please check those out. We've discussed several things in them. First of all, what an inverse is, how to find inverses, and how to show that a matrix even has an inverse, right? Because not all matrices have inverses. In particular, only square matrices have inverses. And even then, not all square matrices have inverses, only some of them do. The way that we discussed on how to show a matrix has an inverse is you would take your matrix, let's say A, and you would RREF it, you'd reduce row echelon form it. And what you should get out of that is the identity matrix. Like exactly the identity matrix. Not something that looks kind of like the identity matrix, but exactly the identity, which means you should get ones along the diagonal and zeros everywhere else. Okay. So if that happens, if when you reduce row echelon form your matrix, you get the identity, your matrix is invertible. And then how you'd solve for the inverse is you do pretty much the same process. You would take your matrix, you'd augment with the identity, and when you RREF it, now the left-hand side you should get the identity, right? Because that's what we expected. And on the right-hand side is where your inverse is. So this is how you find the inverse of your matrix. Take your matrix, augment with the identity, reduce row echelon form it. Okay. And we will show in future videos when we talk about the determinant of a matrix, how exactly another method of showing your matrix is invertible. Okay. Cool. So that's the whole process. That's what we've discussed up to this point. Now we're going to be applying that concept. We're going to be using inverses to solve systems of equations. So say you have just an arbitrary system, AX equals B. This is sort of the whole premise of the course. The entire course is centered around solving this. You're trying to solve an equation that looks like this. So we already know one way, right? The classic way is you take your matrix, you augment with B, and then you RREF it. Right, that's how you can solve it, and that breaks up into three cases. Either there's no solution, one solution, or infinitely many. So this is sort of like the classic way of solving your system. But if your matrix is invertible, there's another way. So imagine this matrix A, imagine it is invertible, so it has an inverse. What happens if we multiply both sides by A inverse? So multiplying both sides by the inverse of my matrix. What happens? So I'm going to multiply on the left. Okay. And remember how matrix multiplication works? You can do it in whatever order you want. So instead of multiplying A inverse by this, we can sort of just move the parentheses, right? It's like A inverse times A, and then that thing times X. But what's A inverse times A? This is where the definition of A inverse, of the inverse matrix is important. If you take your matrix and multiply by its inverse, you always get the identity matrix out of it. But the identity matrix, that's sort of like the one in matrix world. Whenever you multiply the identity by any other matrix, you're just going to get that original matrix. So in this case, I times X is just X. So we found our solution. If we wanted to solve this system, AX equals B, the solution is you take the inverse matrix of A and you multiply it by B. That's what your solution ends up being. So let's see that practice in action. So we're trying to solve AX equals 4, -1, 3. So as we determined down here, the solution to this would be we take A inverse and multiply by 4, -1, 3. And A inverse was given to us. They already told us what it is. We don't have to solve for it. So A inverse is 1, 0.8, -0.4, 1, 0.4, -0.2, -0.5, -0.6, and 0.8. So that's A inverse times 4, -1, 3. And then just recall how matrix multiplication works. We take rows times columns. So when we do the multiplication, and I'm not going to focus on the multiplication in this video, but when we do the multiplication, we get 2, -1, 1. So this is the solution to this equation here. We found our solution. So that's sort of really big reason that inverses are important. They allow us, instead of having to go through the multi-step process of reduced row echelon forming, they allow us to find our solution using matrix multiplication. Now, the question is, well, don't we have to do reduced row echelon forming just to get A inverse? Yes, but there are other methods. Particularly for small matrices, there are sort of compact formulas to find the inverse, but that involves the determinant, so we're not going to discuss that in this video. But overall, yeah, so being able to find the inverse of your matrix is very powerful. It allows you to solve your system a lot quicker than traditional ways. Wonderful, okay. So thank you for joining me. As I mentioned at the beginning, I work for the ASU Tutoring Centers. If you want more information about the free resources we offer on all 4 major ASU campuses and online, check out tutoring.asu.edu. If you want more videos like this that go over specific concepts from your course, or possibly you want to see what upcoming review sessions we have, go ahead and check out this link down here. So again, thank you all for joining me, and have a wonderful day.